Hello, linear algebra student. This video is for chapter 4.3, part 3. We are continuing with bases. So at this moment, we are not trying to figure if this set is a basis for R4. We just want to span it and span these vectors out, and then which one is the minimum that can span that, right? So meaning I am going to do a vector space that is this v1, v2, v3, 1 2 3 4 5, right? v4, v5. So all the linear combination of all these, but which one is the minimum that I should pick so that it would span the same vector space? Oh, I should say this, right? There's a big difference between v equal to this and v equal to span of this. So to do that, I will need to check which one are dependent on each other on the other by doing the augmented matrix of solving ax equals 0, because I will just pretend that they are linear and see if they are linear independent or not, just as if we're checking that. I know that they are not because I have 5 vectors, so at least one of them, maybe more than one, are dependent on the other. But which one? Which one can I kick out, right? So I will do, because I don't want to kick out too much and I don't want to kick out too little, so that it's a base. A basis is like the minimum that you can pick. So I do that, and I do a reduce row echelon, and in my matrix here, so it is really big. 1 0 0 negative 1 negative 2 0. That's the first row, and then 0 1 0 negative 3 negative 3 negative 5. Oh, and then 0. What? Okay, so 1 0 1 0, and then negative 3 negative 5 0. The third one is 0 1 0 0 1, and then 0 2 0. The last one is all 0. Okay, so I claim that the one that is independent are the one with the prefix position. Why? So in a nutshell, you can just do that. So these are just like x1, x2, x3. We have to solve this equation, and this would be x4, and this is x5, right? So because basically you can have x1 equal to x4 plus 2x5, right? And then x2 is equal to 3x4. Remember, we do that in 1.7 plus 5x5. And then x3 would equal to negative 2x5. Doesn't depend on x4. And that's it. So x4 is free. x5 is free, right? So this is a solution. So how can I tell that this column is actually is the independent sets and these are not? We can think of, if I delete this 3 column, I will have a set that is just a linear independent. That's one way of looking at it, because when I do reduce echelon, so this I'm just going through the rows, right? I don't switch columns. So just imagine if I start off not having these, I will have a 1 0 1 1 0 1 0 0 0 1, and then 0 0 0 0. So that is independent. Does it make sense? So you don't really you can also further analyze the fact that x4 and x5, if you give them a number, they can always be a linear combination of x1, x2, and x3, because these are all depending on what x4 has. So whenever you do an x4, you would have x1, x2, and x2 to corresponds to v1, v2, v3. So based on this reason, whenever you see a prefix column here where the one that corresponds to a free variable will indicate that these are not necessary. These are actually dependent on the first 3, right? So they are linear combination of the first 3. So the independent sets I think the easy way is to think of, if you don't have these two vector, you will have a very nice linear independent set of vector. The linear independent set is 1, 0, 0, 1. The one that corresponds to having a prefix position, 1, -1, and the third one, 6, -1, 2, -1. So this is this, and is also the basis for the span of V1, V2, V3, V4, V5. How can I be so sure? Because if you look at how these are set up, whenever I want to have x4 equal to 1, that means I want to have 1 x4, 1 of V4. I would just have put in x4 and then x5, like this is 1, 0 or 0, 1 or whatever that I want. I can always use x1, x2, x3 to form equal to 0. So it means I can find what x4 would be. So that's why these two are not necessary for spanning the whole thing. Okay, so that is how you can find the basis for the for this 5 vector. Okay, let's do a more difficult one where the vectors are not just r something, but is cosine, sine, cosine 2t, cosine t, and sine t. So are they? So first of all, are they independent? Because if they are independent, they must span, right? They must span because they're not dependent on each other. So let's see. Let's solve the equation of cosine t, c1 cosine t plus c2 cosine 2t plus c3 cosine t sine t equal to 0. And t is any number. This is a trig function, any real number, right? So to test that these are okay, we would have t equal to 0, t equal to 0.1, t equal to 0.2. And I think I have, did I have it? Cosine, oh no, it's not the same. So I would do with cosine equal to 0. So I would say, so that corresponds to an equation of C1 times 1 plus C2 times 1 plus C3 times 0 equal to 0. And 0.1, it would be cosine 0.1 plus C2 cosine 0.2 plus C3 cosine 0.1 and sine 0.1. The third one would be C1 cosine 0.2 plus C2 cosine 0.4 plus C3 cosine 0.2 sine 0.2. So if you put this in, now in the decimal calculator, they don't allow sine. So you actually have to like do some, I put a wrong one here. So I think this column is, I have to delete this column. Oh no, I deleted the wrong one. Control V, Control C, does it work? No. Oh yeah, it does work. So can I say I want to delete this column because I don't need cosine. I don't need sine. Can I delete this? Yeah, I get something wrong. So, but yeah, if you want to, you can. Maybe I'll do it in the lecture. So if you want to, you can actually calculate. You actually have to set up a the values of them, and then do RREF, and you see that they are row equivalent to 1, 1, 1, an identity matrix. So that's proof that they are independent. So these threes are independent. You can also look at by inspection. There is no way you can write one in terms of the other, but inspection is like sometimes not very, very straight, or the yeah. So doing this is better. Example 4, I have one matrix V1 and V2, but then H is not spanned by them. H is another set. It's 0, A, and negative A, where A is real. That means it's kind of like all the matrix, all the vectors here are 0, 1, negative 1, 0, 2, negative 2. Can we say V1, V2 is a basis for H? Because obviously I can add this together to get any of them, right? But I would say no, because V1, V2 must be a subset. In order to it to span it, it must be a subset of H. But obviously 0, 1, 0 is not in H, although it can span some of it. And also 0, 0, 0, 1 is also not in H. So you cannot use this to span a set like that. So that would be another basis. I would say the basis will be 0, 1, negative 1, right? So this would span H. Example 5. Find a basis spanned by 5v1 minus 2v2 equal to 3v3 by the set v1, v2, v3. But there's a relationship between them. So we use the spanning set theorem. Spanning set theorem say, oh, the set must have something that is take away the linear combination of the other. So if I have this relationship, that means V3 can be taken out, right? If anyone want to depend on V3, you just write it as 5v1 minus 2v2 divided by 3, and that would replace it. So you would say the set that is a basis would be just be V1 and V2, right? Assuming that V1 and V2 are actually linear independence. So this should be, because if not, then you don't write it. So this set is a basis for H equal to span of V1, V2, V3. So that means you don't need this in the base to span the whole thing. You just need these two. Okay. Okay. So some interesting example in the book, I just copied here, is about some example of linear independent versus spanning. Just be reminded, if you have n times n like 3 by 3, and they are linear independence, then they are a basis because you can use IMT. If you have 4 vectors, they cannot be a basis because they are linear dependent. And if you have 2, you cannot span out 3 because you don't have enough prefix position in all rows. So these are just very easy way to spot linear independence as well as spanning properties. To check linear independence for these two, you would just check multiples of each other. So that's it. In the next video, we'll talk about basis for 2 particular space. One is the null A, and the other is the column A. Okay, will be in video 4.